All right, thank you for the introduction, and thank you for the organizers for inviting me. Yes, I'm Ravi Naik. I'm a research scientist at Berkeley Lab and the head of measurement for the Advanced Quantum Testbed. Today, I'll give a talk that perhaps argues more related to digital quantum computing than maybe something that's beyond the gate model. But I think a lot of the physics and the underlying ways we realize the gate that I'll describe can be used for beyond gate model interactions, and I'm hoping to show that we have a good platform for working with these systems that could be encouraging for future projects and collaboration. So first, I'd just like to show our team here. We have a lot of people working on these projects with a variety of backgrounds and expertise. And they all contribute in different ways to the testbed and other projects at both Berkeley Lab and UC Berkeley, led by Irfan Siddiqui. So I just want to give a little bit of a briefer for the Advanced Quantum Testbed in case people are not aware of what we are and what we can offer. So what we have is a unique quantum platform that we want to make available to the wider community for scientific exploration in all aspects of quantum information science. The way we want to do this is through deep user collaboration, where we have a open proposal process where users can come to us, work with us deeply to use our full quantum system. To do this, we really want to employ a broad exploration of technology, not really focusing on one particular thrust of superconducting circuit-based quantum information, but really do a broad exploration so we can really understand what the technology has to offer. And importantly, we want to develop experts in the field who understand these devices, can use them, and can work with users as well. We work on the full stack of superconducting quantum computing platforms. That includes the cryogenics that we need to cool down our devices, along with the circuitry involved in those. The processors themselves, which I'll talk a little bit more about later. The software stack, including compilation layers that may be relevant for specific types of quantum simulation problems, for example. And importantly, the commercial control hardware. We heard a little bit yesterday about Cubic, which is our open source quantum control hardware platform. We really need these types of controls to be able to realize maybe sort of more interesting or exotic types of controls and interactions that would be necessary for quantum simulation. So jumping in a bit to our processors to give an overview of not just the processors themselves, but our philosophy behind how we work on this type of science. In the first phase of the AQT, so the AQT is about a 5 to 6 year old program at this point, we developed several different types of processors, and they fit sort of on this graph that represents our approach to sort of broadly exploring the types of technology we have. I will clarify that all the base qubits here are transmon-based qubits, which are the standard qubit typically used in superconducting processors, but we are also looking at novel types of processors that we can integrate into these multi-qubit designs. On the left, we have on the right, we have our Trailblazer chip, which is a sort of bare bones system where we have fixed coupling between fixed frequency qubits. So it's a very constrained system, but in that sense requires minimal control, simply a single control line per qubit. And through multiplex readout, we're able to read out all 8 qubits simultaneously. This makes it very efficient in terms of the hardware we need to control it and operate it. And because of the limited potential loss channels that we introduce through these control lines, this is our most coherent system, allowing for the highest coherence times. On the left hand of the spectrum, we have the SpiderNet processor, which has 8 qubits that have all-to-all connectivity via a shared tunable superconducting bus. This bus resonator is both tunable as well as all the qubits there, allowing for a highly reconfigurable processor. Because of this additional complexity, this introduces additional sources of noise and errors, leading to some sacrifice of the coherence. But for certain applications, perhaps having this higher connectivity at the sacrifice of coherence is a worthwhile trade-off for exploration. And we're looking at other designs, along with our collaboration with MIT Lincoln Labs at tunable qubits, and actually the type of processor that we're looking to really expand in the future, fixed frequency qubits with tunable coupling between them. And we wanted to do these explorations before we really thought about scaling to larger size processors to really understand and gain lessons from each of them about what works and what doesn't. And that's what informs future design as we move forward. I won't go through all of them, but I do want to deep dive a bit on the processor that we use for the experiments that I'll describe later. That is this fully fixed frequency system. Here we have coherence times in the order of about 100 microseconds for T1 and T2 for these qubits. And with this, we've been able to do extensive, in-depth investigation of what we can actually do with this processor. To enable this, we focused on realizing high fidelity readout of not just the qubit states 0 and 1, but also we call Q-dead states 2 and even beyond here, which allow us not only to monitor leakage outside computational space, but we actually utilize these higher energy levels for computation. In terms of quantum control, we've been able to realize high fidelity single and 2 qubit gates, including a novel type of 2 qubit gate developed at UC Berkeley that is based off a differential AC Stark effect. And these gates, importantly, are only between nearest neighbors on this chain, and these interactions between these nearest neighbors are mediated off-resonantly by a resonator. And you can see that they're in a ring geometry where these resonators at the top and bottom connect this ring around here. The real highlight of utilizing this processor, though, is this last bullet here, where we've been able to unlock capabilities that maybe naively you would not expect to have with such a processor. The one I will highlight most today is being able to realize in a single step a 3-qubit gate with only nearest neighbor connectivity here, a iToffoli gate, which is a variant of the Toffoli, with extremely high fidelity over 98%. And I'll go through that in detail, so I won't spend too long on that. But two more things that I want to highlight that may be relevant for quantum simulation, both digital and analog. We've really focused a lot of efforts on being able to utilize the extra quantum resource that we have, namely that these transmon qubits are not qubits at all. They're Q-dits. They're many-level systems, and these higher levels can be coherent and accessible. So if we have this resource anyways on these processors, perhaps we should try and utilize them to be able to have a much larger Hilbert space in a smaller device. But to enable that, we need to have controls that we understand and be able to do with high fidelity. In that vein, we developed a 2-qubit entangling gate, CZ gate, which is maximally entangling the 2-qubit space with fidelity over 97%. And in addition to that, we've been able to realize interactions that naively you would think that we'd not be able to do with a completely fixed frequency system, namely Heisenberg interactions, which we can utilize to realize all types of different types of gates, including I-swap gates in this completely fixed frequency system with fidelity over 99% here. These Heisenberg interactions really rely on our understanding of the controls that we apply in a Fouquet formalism. And in this effective space, that's where we can, when I say Heisenberg interactions, really it's in this effective space. So now I'll move on to the bulk of my talk, which is be focused on this 3-qubit iToffoli gate that we realized. And one thing I want to emphasize that we were able to do this by taking advantage of controls, in particular that are realized from non-commuting interactions. And this work was led by Joseph Kim, who is now a professor at Korea University, and Long Win, who has very recently, just in the past week, joined Amazon. And here's a citation if you'd like to look up. So just to give a refresher for those that may not be super aware, the Toffoli gate is a 3-qubit gate, and it is both important in not just quantum computing, but in classical computing. Is a key element of realizing a universal reversible classical computer, and is a universal quantum gate if you have just a Hadamard here. So importantly, the Toffoli is not a Clifford gate. That's why you're able to realize a universal gate set with just a Hadamard here. One challenge, though, it is like many 3-qubit or n-qubit gates, it is quite challenging to realize if you only have single and 2-qubit gates, especially if you have a system that has limited connectivity with, such as our system that I showed before. In our case, we have nearest neighbor connectivity, so to be able to realize this, we would need 8 2-qubit gates, not to mention different single-qubit gates as well here. So this is a interesting gate for a lot of quantum computation, but it's very difficult to realize. Now, why is it useful? You can realize a number of different applications. This here is a circuit for a quantum adder circuit. I won't spend too much time on all these. It can reduce some of the computational complexity in terms of gate count and circuit depth for factoring algorithms and a number of other algorithms, and can play a role in quantum error correction. So this is a gate, a lot of interest in the community in general, but can be very challenging to realize. Now, what I'll talk about is actually not the Toffoli gate, but the iToffoli gate, which is a minor variant of the Toffoli gate here, where there's an additional phase on the element that is sort of the not part of the Toffoli gate. So this is just a clarification here, and I'll talk a little bit about the differences between these two a bit later. Now, I'm going to go dive into the device physics on how we actually realize this gate. To understand this, first I want to focus on this 2-qubit interaction here, known as the cross-resonance effect. The way I like to think about the cross-resonance effect is effectively utilizing a qubit as a quantum filter for signals. So if we have a signal here that we apply, so this is a microwave signal at a particular resonance frequency, which we choose to be equal to the resonance frequency of this target qubit. Now, if we had this signal directly applied to the target qubit, what we'd realize is Rabi oscillation, so being able to effectively have a X drive on the target qubit here, and that rate of the X drive is determined by the amplitude of the signal that is passed. Now, instead, if we have a 2-qubit system where we have a control qubit set a different frequency with some complex constraint G between the control qubit and the target qubit, what role the control qubit plays is effectively filtering this signal. Because this control qubit is a resonator, it plays a role of a resonant filter, an off-resonant filter for this signal here. But the effective transmission of this filter is dependent on the state of the control qubit, because the control qubit that we use here is based on the transmon, which is an anharmonic oscillator. What that means is that depending on the state that you're in of the control qubit, the effective resonance frequency shifts. This plays the role of a nonlinear filter for the signals that are coming in. What we get then is conditional Rabi oscillations on the target qubit, conditioned on the state of the control qubit. What that means in terms of a Hamiltonian parlance, an effective Hamiltonian parlance. So I want to clarify for anyone in the audience that this is an effective Hamiltonian. We get a ZX Hamiltonian. The Z being that depending on the state of the control qubit, so 0 or 1, the effective Hamiltonian we get changes the sign of the drive that is applied to the target qubit. So we can oscillate in one direction or another here. We can also change this in different ways if you add additional, if you'll see in a lot of literature, there's an additional IX term as well, which means that the effective rate of Rabi oscillations is changed by this conditional term. This is what we'll utilize to realize the iToffoli gate. Now, if we expand our system to a 3-qubit system here, and again, these 3 qubits are in line and with only nearest neighbor connectivity. So now what we'll do is actually drive both of the qubits. So first, we have a drive related to driving the control qubit here. There we go. We'll also drive the second control qubit on the right here, and so we get a ZX term here and a ZX term here. And then finally, we'll have an additional drive directly on the target qubit. So a few things I want to note here. All of these terms are either 2-body or 1-body here. So there's no actual 3-body term that we're driving if you break up these terms individually. Secondly, these terms here actually commute with each other, as well as this IX term here. But by controlling the phase of the drive here, we can have a additional Y term here, which does not commute with the other 3 terms here. This is key for actually being able to realize the 3-qubit gate. If we had only commuting terms, there is no way to realize a sort of non-trivial or 3-body interaction with just single and 2-body terms. So this is the actual physical system. We have 3 qubits here and 3 control lines that we'll apply drives to. To understand what happens when we apply this effective drive here, we break down the Hamiltonian in terms of the action on the target qubit. We do this because the control qubits, because we're driving them off resonantly, the only effect on them is an effective phase that is applied to them. But the target qubit, because they're driving on resonance, experiences Rabi oscillations. And these Rabi oscillations, which are given by the X and Y Hamiltonian here, are conditioned on the state of the control qubit. So in this terminology, conditioned on the control qubits being 0, 0, 0, 1, 1, 0, and 1, 1, we get a different effective Hamiltonian on each of these states. And if we choose the effective Hamiltonian terms, alpha, beta, gamma, and delta, which just correspond to amplitudes of the drive, as well as a phase to get the ratio of gamma and delta here, we can realize specific conditions. Namely, what we want is that the effective Rabi rate of one of these states to be different from all of the rest. Right? So that means only for one of these states, the oscillations will be different. And if we choose this particular condition here, I guess actually two conditions, where all three of the x amplitudes are equal, and the y amplitude is the specific ratio of them, then the effective Rabi rates will be given as follows. And what we'll show here is that if we have that, then we get oscillations about the Bloch sphere for the target qubit that are conditioned on the control qubit. And if we chose those specific amplitudes for the 1, 1 and 0, 1 plus 1, 0 state, if we wait a certain time such that they do a full 2 pi oscillation around the Bloch sphere, what happens when the control qubits are in 0, 0 is that we get a 3 pi rotation. So we actually get a complete flip on the Bloch sphere for the target qubit, thus the NOT gate. So this is how we can realize this conditional NOT on the target qubit. So that explains the action on the target qubit. We additionally apply some phase such that instead of having this x plus y, we can convert it to an ix. These are just local z gates that are applied virtually. So they actually have no additional cost. So this is just changing the frame for that target qubit. When we actually apply this drive, so this is data here, we see the action on the target qubit. So that's what we're measuring here. This is the z projection for the target qubit, conditioned on the control qubits. And we can see that we do realize this conditional Rabi oscillation where if the control qubits are in 0, 0, we get a different rate for the oscillations. And if we wait until a time around 353 nanoseconds, we realize a complete knot on this 0, 0, condition on this 0, 0 state here. And that's what we'll actually use for our gate. To benchmark it, we can use a number of different methods. For visual clarity, we can look at this truth table here. So this is simply a classical benchmark of the Toffoli gate, but it is informative for seeing clearly that we had this Toffoli-like interaction. But to more rigorously be able to benchmark this gate, we use a method called cycle benchmarking, where we alternate our gate of interest with a randomly selected set of Pauli gates here. We chose this method because the iToffoli here is not a Clifford gate. It can be generally difficult to compile 3-qubit Cliffords in general, and is not a very effective method to use standard randomized benchmarking. But cycle benchmarking only relies on having a single layer of Pauli gates here. For different choices of Pauli's before and after here, so essentially preparation and measurement bases, we get a number of different effective decays. And if you take the average of these with and without the interleaved iToffoli gate, we can get an effective average gate fidelity for this gate. And we realize in the single step iToffoli gate over 98%. Now, if we were able to compile this iToffoli gate in terms of the single and 2-qubit gates that we have measured for this same device, otherwise, the fidelity would be closer to about 95%. So there's a significant improvement in that, and in large part because we were able to do it in such a short period of time, 350 nanoseconds. In terms of error budget for the system, we see in this orange line here the effective coherence limit. Now this is an effective coherence limit when the drives are on. We do see that there's some reduction in the coherence due to these drives. And additionally, there's a a phase error that occurs at stronger drives, and it becomes more the dominant source of error as we do. Essentially, if we look at the oscillations before, we see that some of them don't completely reach all the way to 0. So this is due to an unwanted ZZ error between the control qubits and the target qubit that results in tilted Rabi oscillations and leads to a coherent error here. We do think that there are ways to mitigate this additional coherent error using off-resonant drives. But the takeaway here is that we're able to realize a high-fidelity, non-trivial 3-qubit gate that would otherwise rely on native 3-qubit interactions, just using 2-qubit interactions and being careful about how we actually drive the system. And just to take a step further about looking at the power of such a gate, we did some numerical experiments looking at what we can synthesize using this 3-qubit gate, whether the fact that we have an iToffoli versus a Toffoli makes a difference for that. And what we realize is that the iToffoli and the Toffoli effectively have quite similar power in terms of being able to synthesize arbitrary 3-qubit Clifford and Har-random circuits. And for Cliffords, you would require 6 of these iToffoli gates, and for Har-random, 10. And then we're able to do that with 100% success rate. Now, this is just the 3-qubit gate and arbitrary single qubit rotations. Interestingly, as we were doing this investigation for synthesizing arbitrary Cliffords and unitaries, using these gates, we took a look more generally, if we have a Hamiltonian of this nature, what happens if we actually sweep this relative phase, this yt. So this is the degree of that we have this additional non-commuting part of our drive. And while for the Toffoli and the Clifford here, we're able to realize Har-random gates with a circuit depth of 10, there's actually a regime here where we only need 9 of these 3-qubit gates, which I can't really describe what exactly they are, to realize arbitrary Har-random gates. What this elucidates to us is that this is actually a really general protocol. I wrote these specific terms here for the cross-resonance interaction and local gates, but you could have any types of entangling interactions. And if we're careful about how we combine them, and you take advantage of the fact that if we use non-commuting drives, we can be able to realize a whole class of many qubit interactions. And I think we take this a step forward, looking at beyond even 3 qubits to many body interactions that could be relevant for a lot of quantum simulation. And I think what this elucidates is that we don't need these particular special types of gates like Toffolis or C-naughts or anything like that we use sort of program to understand for gate synthesis, but really something more general and maybe not intuitive to realize interesting interaction, explore entangling space, which I think could have implications for applications beyond gates as well. How am I doing on time? Okay, so I'll just quickly finish with an explanation of our user program in case anyone's interested in future collaboration. So we want to offer an open quantum resource to the general community, and we want to offer it for no cost as well. So as long as you have support for your own scientific directions, you can apply to be able to use our quantum processors to pursue a collaborative experience with us. So we want to be as flexible as possible in both the proposal process and the experiment itself. So we want to deeply engage with the users to find the best path forward for collaboration. We want this process to result in an exchange of best practices. So we've had a lot of experience ourselves with our internal science, understanding these processors, working with them so deeply. We want to expose that to our users so that they understand how they can best take advantage of the resources that are available and what challenges remain. And we also want this to occur between users as they use our processor. And we want the students, postdocs, research scientists in our lab to work with their counterparts in the user community and collectively develop a QAS workforce that can be necessary moving forward. The proposal process, we want to be as streamlined and light as possible. So what we ask is initially for a letter of intent, 4 brief paragraphs, so a single pager on a description of the project and the team that will be involved. That goes through a screening internal to our team where we have some level of downslide depending on our resources and our capabilities and understanding of the project. But in this process, we often reach back out to the users to get clarification, understanding of what goes on. And after that, we ask for a full proposal, which again, only 2 pages, and often has a description of the team itself. In the interest of full transparency and fairness, we went to both internal and external review of this proposal, and then we choose proposals depending on our resources that we can run at the testbed. I will note, because I don't think I noted before, we are one of 2 DOE testbeds, including we are the superconducting-based one, but there's an ion trap-based one at Sandia called QScout. In terms of how the project actually goes, we want this to be an involved process. So we want to work with the user team to scope out the project itself, not just be able to rely on, say, some cloud resource where we're not involved in the process. And depending on our availability and also the availability of the processors that we have, we execute the experiments on the AQT testbed, and we want to do this in close collaboration. And this could come in a lot of different methods, depending on how involved the users want to be directly with the experiment. And our goal is to have joint publication between the teams. We've worked with all kinds of institutions, in the United States and abroad, including academic groups, national labs, and industry groups. We have no restrictions, with the exception of a few countries, on who we can work with. So I certainly invite anyone who's interested to reach out. In our next phase, so we just started our second phase of the testbed, we really want to expand both the capabilities that we have, but the user community as well, and be able to interact more in depth, including having some in-person access. We've actually had some grad students stay with us for a month to be able to interact more closely with the experiment. And if you're interested, please check out aqt.lbl.gov and specifically the user program tab here. Right now, we've opened up our user call. This is a nice time to be able to get an LOI in because we can collect and take a look at many different types of many LOIs simultaneously. So this is the best chance for being able to really start getting involved. All right, thank you. I'll say that the optimization that we used for this gate was a bit manual. I wouldn't say we went super hard. I think we could probably eke out a bit more if we use some kind of numerical optimization. I think largely the leakage is limited because the strength of the drives that we use are relatively small compared to, one, the anharmonicity of the qubits. So this is the difference between these higher energy spacings and the fundamentals that we use, as well as the detuning between the qubits. So the drive strength is small relative to those. I think if you went to stronger drive strengths, so faster gates, then leakage would become more of a dominant error source. Yeah, so I think that's always the case with especially these transmon-based processors, because in essence we have a weak harmonic oscillator, which is about 10% anharmonicity, or 5% actually, I should say. And so anytime we try to push the gate speed, we have to take that into account. I think pulse shaping could play a role there. You can essentially use pulse shaping to transform the Fourier, the effective Fourier spectrum of your drive such that you can minimize the amount of leakage using that. Other groups have also looked into ways of using what they call leakage reduction units, where you have leakage over the course of your algorithm, but then you use that to suppress it. But that would perhaps be challenging to do, say, in an analog's case.
This isn't exactly my field, so I'm not sure if this is a trivial question, but the gate phase error seemed like it was decreasing. The iToffoli, the gate phase error seemed like it was decreasing as you get to a larger iterations. Is that the expected behavior?
Yes, so we believe that this unwanted gate phase error, which is results from an off-resonant driven interaction between the qubits, gets stronger as we drive harder, and that means for shorter times we have a higher amplitude for the gate, but at longer times we have a smaller amplitude gate, and that error becomes smaller. So at longer gate times, it does become smaller. So that is the expected behavior.
So the gate time, what is the gate time representing the duration? It's like the duration that you're under which you're processing the gate.
Yeah, so we apply the drive for a certain period of time, and the time it takes to realize this oscillation, this, I guess, 2 pi for 3 of the states and then 3 pi for the last one, the time it takes to apply that drive, the time we have to apply that drive to realize that full oscillation sets the gate time. And the harder we drive, the faster we can do these oscillations, the shorter the gate time. And so we can control the gate time by controlling the strength of the drive that we apply, which in turn controls the strength of those Hamiltonian terms, the coefficients in front.
Yeah. Thanks for the talk. I want to ask about this, comparing some arbitrary three-qubit gates with this optical. I think in this topic part, you show that actually this very good fidelity. I think large part is coming from this cross-resonant effect, which is analog Hamiltonian type illusion. I wonder why we don't use this kind of analog, just by controlling the pulse to generate some arbitrary three-qubit gate instead of compiling it using this fixed.
That's a good question. I think we should. I think that's what sort of the experiment here is showing, is that, I mean, it is sort of an analog approach to realizing a digital gate in the end. But when we break it down into single and two qubit gates, which is generally done, and there's a good reason for this, because I think when we're trying, as I speak from sort of the hardware perspective, as few things that you need to calibrate as possible, the easier it is to be able to realize the processor. And if you can do universal quantum computation with just single and two qubit gates, then you can spend all of your time just on calibrating single and two qubit gates, especially if you can do things like quantum error correction with just those elements here. But what I think is, if we introduce additional elements, and there's been some work on this of being able to introduce perhaps a more extended gate set beyond just the base universal gate set, can add a lot of power to the compilation side, especially if we go beyond 2 qubits, where there are a lot of open questions on how to efficiently compile circuits beyond 2 qubits. And so I think just in the hardware community, really focused on single 2 qubit gates because you can realize universality with them. But being able to have these additional resources, which we of course realize through these analog means, can be a boon to that. I'm not sure if that answers your question, but that's sort of my perspective.
Last question?
Sure. So I don't know, did you see my talk about applications? Yeah, so I'm mostly interested in use cases that maybe have hope of some kind of scientific impact. When I look at the test beds, the systems seem small enough that we can emulate. You could make and simulate a quite perfect version of that computer. So can you tell me when it comes to this collaboration, user program, like what is a proposal that is really exciting or an example of ones that, yeah, we really got to do that together with people?
So yeah, the test beds we realized, I mean, we're still using transmon-based systems, and I agree that the processor size, we're on the order of 10-ish qubits. So we're not something that is sort of beyond classically immutable. I think the exciting thing is taking advantage of, I think there's a lot of rich resource available in these processors, and being able to take advantage of that and develop new tools for these processors that could be applied to, say, something that is a larger scale, that maybe something with a lot more resources could have. I think the test beds are a great place to be able to test those that, it can be challenging to do, say, on a commercial processor where you don't necessarily have that level of access. That's one place I think there's a lot to do. A second is understanding in depth what's going on in these processors. My belief is that no matter what problem we're working on in the community right now, errors are probably the most important thing that we need to understand and work on. And what we can do in the testbed, while they're sort of at modest size, enough to start looking at what types of errors start affecting these systems. And we're hoping to grow, say, maybe double the size of our processors very, very soon, understanding how these errors affect processors at scale by looking at the in-depth physics of the processors themselves. And I think the test beds are a great place to do that, where I don't think you'd be able to get that level of access on a commercial system. And if we can understand the physics behind a lot of those, then what we really want is to be able to reduce error rates. And hopefully this is something that we can publish openly, and something that can be picked up for people that are interested in really scaling to larger systems. So I think those are places that I think really benefit a lot. I think there's also things where people want to test something kind of strange, something odd, an approach, say an analog simulation, that can be challenging to realize on a commercial processor, or you just necessarily don't have access to that. This can be a place to try and test that out, or we can work together on, say, co-designing a specific processor to be able to realize that. These are, I think, projects that could look into it. We're not interested in competing with commercial entities in any way, so we want to offer novel resources and deep access that pushes the entire field forward, sort of from a base fundamental physics level.
Great. All right, let's thank the speaker, Ravi, again.